Hello everyone. In the last video we have seen a solution of Fredholm integral equation of first kind, and for that we have used the uh, Hilbert-Schmidt theorem as well as the Reyes-Fisher theorem. Okay, so today we are going to start with a new topic, that is singular integral equations. Singular integral equations. An integral equation is called singular if either the range of integration is infinite or the kernel has singularity within the range of integration. Okay, within the range of integration. Now let us look at some examples to understand what is this singular integral equation. Okay, so for example, let us consider the first equation as f of x equal to integral from 0 to infinity sine of xt yt dt. Okay, so you can clearly see here this is the integral equation of the first kind. Okay, and this is sin xt is the kernel kx comma t, and the integration limits are from 0 to infinity, and therefore this becomes the singular integral equation. Okay, let us look at one more example. F of x equal to integral from 0 to infinity e raised to minus xt yt dt. Now this is also same as example 1. Okay, the integration limits are infinite and therefore the equation is a singular integral equation. Now let us look at one more example. See, example 1, example 2, all are, even the example 3, all I have taken them as the integral equations of the first kind. Okay, but when we come to singular integral equation, we usually don't say the first kind and the second kind thing. We just say that it's the singular integral equation. Okay, now let us look at this. This will give us the example integral from 0 to x y of t divided by root of x minus t dt. Okay, and t is varying from 0 to x. Okay, so for this, when t becomes x, what will happen? The kernel kx comma t, which is 1 upon root of x minus t, okay, that will become indefinite. Sorry, it will become not defined. Okay, so it will have a singularity, and therefore this equation is a singular integral equation. Okay, now in our syllabus we will be studying one special kind of integral singular integral equation which has a name that is called as the Abel integral equation. Okay, so let us start with that. the solution of Abel integral equation. Okay, so consider f of x equal to integral from 0 to x y of t divided by x minus t, this full thing raised to some alpha is a constant, okay, dt, where this alpha is taking the values between 0 and 1, open interval 0 1. Okay, so here the conditions are where f of x is known function. Okay, so you can see here this f of x, whatever you can see in the LHS, it is a known function, while y of t is to be determined. Okay, because what is y of t? Y of t is the solution of this above integral equation. This y of t is a solution of this particular integral equation, and we want to determine what is that y of t. Now let me name that equation. Okay, the above equation, the above integral equation is the integral equation formulation of the problem in mechanics. Okay, there is one problem in mechanics where a material point is moving under the influence of gravity along a smooth curve in a vertical height x, okay, fixed point to a fixed point 0. Okay, so there is some material particle and which is moving along a curve at this fixed height x. Okay, and for that particular thing, it is a problem which comes under you can say physics or mechanics. Okay, so that problem, it is framed in terms of integral equation, then that particular integral equation of this particular problem will look something of this form. Okay, whatever I have written just now. Point 0 on the curve, okay, and this takes the time f of x. Okay, so for alpha equal to 1/2 above equation is the integral equation of this problem. Okay, so whatever this problem of mechanics I have written here, for that problem of mechanics the integral equation representation is given by this equation. Okay, and 0 to x, what it is already mentioned there, and f of x is a known function and that is the time taken. Okay, and this alpha value should be equal to half. So if all these things are done here, then this integral representation this integral equation represents that particular problem in mechanics. Okay, now there is a nice way in order to see how we can for this problem in mechanics, how we can derive or how we can come to this integral equation. Okay, like for Brachistochrone problem, whatever we study in calculus of variations, there is a theory and physics involved behind that. So by using that we can actually come to the Brachistochrone problem, whatever functional we get. In a similar way here also, by using some physics and mechanics whatever is there and mathematics, we can nicely come to the integral equation, but that theory part is not there for you. Okay, we will be interested in only finding the solution of this particular equation. So whatever this mechanic problem is given to you is just for your information. Okay, to understand like what are we actually studying or where it is used. Okay, so we are interested only to find the solution of this equation. So now to solve this equation, that is f of x equal to integral from 0 to x y of t x minus t raised to alpha dt, where alpha value is between 0 to 1. Okay, to solve this equation, let us name this equation as 1. To solve the equation 1, I will multiply both sides of equation 1 by the term 1 upon u minus x raised to 1 minus alpha. Okay, multiply both sides by this term. So what we will get? So I will, and once I multiply with this, then I am going to integrate it with respect to x from 0 to u. Okay, I will integrate it with respect to x and the integral will be from 0 to u. Okay, this is what we will do now for this equation. So what it is, how it will become? Integral from 0 to u. Okay, f of x is already there and we multiply this term, what it is, u minus x raised to 1 minus alpha into dx. Okay, this will be equal to integral from 0 to u, okay, dx, but inside what we have, we already have this multiplied term, that is u minus x raised to 1 minus alpha into this term, what it is, 0 to x y of t by x minus t raised to alpha dt. Okay, this term is already there. Now you see here 0 to x are the limits of which variable? Of the variable t. T is going from 0 to x, and 0 to u are the limits of which variable? X. Okay, so x is going from 0 to u. Now changing the order of integration, on the right hand side of equation 2 we will get the following. But before that, let us see how we can change this order of integration. So this is the axis t and this is the axis not this t and the x. Okay, we have two variables, no? Integration variables are x and t. So I am drawing those two axes and now I will change the limits. So initially x is varying from 0 to u, okay, and t is varying from 0 to x, okay. And now we will change. So let me draw this figure. So first let us draw this line, that is x equal to t. This line is what? X equal to t. So where will be u? U will be some x is varying from 0 to u. So this is 0 to u I will have to go. Suppose this is point u. Then if I extend this vertical line, can you see at this point I will get this u comma u, okay. So x is varying from 0 to u, and that means x is varying in this region. See, and where t is varying from 0 to x. So t is varying from 0 to x. So it is x is this line, no, x equal to t, the one which you can see in blue color. Okay, so x is varying from, sorry, t is varying from 0 to x. So it is over this. So the common what is the region of integration? Our region of integration is nothing but this triangle. And now we will change the limits of integration. So initially x was varying from 0 to u, right? So now let us vary t from, now t will vary from 0 to u, and x will vary from where? X will vary from 0 to x will vary from t to u, okay. X will vary from t to u, okay. So now if you observe this also, if you try to plot this particular region on the graph, that will also come out to be the same triangle, okay. So let us see that t is going from 0 to u. So where t is varying? T is going from 0 to u. So t is taking all these values. U is this line, right? So t is varying from 0 to u. It is taking this, and then x is varying from t to u. So it is this t to u. So we will get this region. So the common region of integration will be what? I think initially when I said that x is varying from 0 to u, I think I plotted those red color lines. I took them on top of this line, right? So x is varying from 0 to u means what? It should vary from oh no, sorry, yes, I was correct, no, that is correct whatever I said, okay. So yeah, that is done. And here also you can see that in this box whatever is written, that region also if we plot here on the graph, we get the same triangle, okay. So we have changed this limits of integration, and after doing this we will get in the above in equation 2, how equation 2 will look like? It will look like integration from 0 to u f of x divided by u minus x raised to 1 minus alpha dx will be equal to integral t will vary from 0 to, I am taking this dt outside and dx inside, okay, because the limits of integration are changed. T will vary from 0 to u, so it will vary from 0 to u, and I will get here y of t and here dt, okay, and inside here what it will be, integral x will vary from t to u, x equal to u, and inside the integral I will get this term u minus x raised to 1 minus alpha x minus t raised to alpha, okay, into dx, okay. So this is the new equation that we have. Now we will have to calculate what is this integral, okay, and then we will try to find out what is this y of t, okay. So let us first simplify this integral I, whatever is there inside the bracket. So now let I be equal to integral from x equal to t to x equal to u 1 divided by u minus x raised to 1 minus alpha x minus t raised to alpha dx, okay. So we will use some substitution. Let u minus x divided by u minus t be equal to some s, okay. Then if I am using something inside the substitution for the integration, then what are the three things that should be changed? These limits will change. Then inside the integral sign, wherever this term is there, that is u minus x divided by u minus t, so wherever that term is there, I will have to replace it by s, and this dx should become ds, okay. So let us do all those changes. So then from this what will be x equal to? X will be equal to s into u minus t, so u minus this, okay. So x will be equal to this, and that will imply what? Dx will be equal to minus u minus t into ds, okay. So these are the substitutions that I will make, but how the limits will change? So when x is equal to t, s will become what? S will become 1, and when x is equal to u, s will become 0, okay. So we will get I to be equal to integral from 1 to 0. In place of dx it will be minus u minus t into ds divided by, now u minus x raised to 1 minus alpha is what? This will be s, so u minus x will be equal to s into u minus t, and this thing raised to 1 minus alpha. So what we will get? S raised to 1 minus alpha, u minus t raised to 1 minus alpha. Then in place of x what we have to put? U minus s into u minus t minus t, and this full thing raised to alpha. So this will become, I will change the limits of integration because there is that negative sign, so this will become limit integral from 0 to 1 ds divided by s raised to 1 minus alpha u minus t raised to 1 minus alpha. And what will this become? This, after simplifying, it will be u minus s into u plus s into t minus t. Okay, but this I can write it as u minus t. This I can write it as u minus t. Okay, minus s into u minus t. Then again I can write this as u minus t into 1 minus s by taking u minus t common out. Okay, so this term inside the bracket can be written as u minus t into 1 minus s, and then this full thing raised to alpha. So what I will get here? So here I will get this as u minus t raised to alpha 1 minus s raised to alpha. Okay, so and on top it is ds into u minus t. So now you can see, in fact everything will get cancelled, because u minus t raised to 1 minus alpha, and this is u minus t raised to alpha. So minus alpha plus alpha will go, only one u minus t will remain, but that u minus t will get cancelled with the numerator u minus t. Then in the denominator we will be left with integral from 0 to 1 ds divided by s raised to 1 minus alpha and 1 minus s raised to alpha. Okay, so this we can write it as, so I will be equal to integral from 0 to 1 s raised to, it is 1 minus alpha, no? So if I take it in the numerator, it will be alpha minus 1. Then second term is 1 minus s, so that will become minus alpha. Okay, but minus alpha I can write it as plus 1, and here minus 1, add and subtract plus and minus 1, and now I will combine this. Okay, so here I will get this as, and if you observe this, this is nothing but beta of, if you remember the beta and gamma functions, okay, this is beta of alpha comma 1 minus alpha. Okay, this 1 minus alpha and this alpha. Okay, so this is beta function of alpha comma 1 minus alpha. But what is the relation between beta and gamma function? The relation between beta and gamma function is beta of alpha comma something is gamma of that something into gamma of that other thing divided by gamma of alpha plus 1 minus alpha. So this is equal to gamma of alpha, gamma of 1 minus alpha divided by gamma of 1. Okay, and gamma of 1 is nothing but 1. So this is nothing but pi divided by sine of alpha pi. Okay, now you may not remember this when but you have definitely studied this somewhere in your TY class. Okay, that property of beta and gamma functions. By using that I have written this, and there is one standard identity which tells you that if you have anything, let us suppose say m also, into gamma of 1 minus m, that is equal to this quantity, that is pi by sine of alpha pi. Okay, so there is this identity, you can go back and check on your with the meaning, you have already studied this. Okay, so therefore this quantity will become equal to pi divided by sine alpha pi. Okay, so now we have, now what do we have from this? What is I? See, we have evaluated what is this quantity I. Okay, and that comes out to be equal to pi divided by sine of alpha pi. So we are left with this. So I am going to write this equation now. So that equation will look like integral from 0 to u f of x into dx divided by u minus x raised to 1 minus alpha is equal to integral from 0 to u y of t dt into pi divided by sine of alpha pi. And pi divided by sine alpha pi, these are the constant terms. So I will take them on the other side and I will get integral from 0 to u y of t dt. I will rearrange the above equation and write it. So I will get this as sine of alpha pi divided by pi into integral from 0 to u f of x dx divided by u minus x raised to 1 minus alpha. Okay, so now we want to find out what is y of t. So definitely what you will try to do, you will try to differentiate this particular thing with respect to u. Okay, so let us differentiate with respect to u. So what will happen for the LHS? We will have to use the limits of the Leibniz rule. Okay, so when we use the Leibniz rule, it is what? Partially differentiating with respect to u this quantity, integration with respect to u y of t dt. So this is equal to, now this is a constant, so I am keeping it outside, sine of alpha pi by pi, and this is differentiation. In fact, not the partial differentiation, I am differentiating complete derivative. Okay, once you apply the Leibniz rule, then it will become the dou by dou u. Okay, so this is d by du of integral from 0 to u f of x divided by u minus x raised to 1 minus alpha dx, and this. Okay, so here when we apply the Leibniz rule, what we will get? Here we will get this. So once we take this d by du inside, it becomes the partial derivative, so that will go to 0 because we don't have any function of u here inside the integral sign. In the LHS I am talking about this. Okay, so first term will go, then the second term, what it will be? Evaluating y at u into du by du minus evaluating y at 0 into differentiating 0 with respect to u, and this will be RHS will be equal to sine of alpha pi by pi, and let me keep it as d by du. Okay, so du, then this is f of x by u minus x raised to 1 minus alpha into dx. Okay, so it is this equation. So what will this equation become? It will be nothing but y of u equal to, because y of 0 is 0, so second term will also go. Okay, and we will be left with this, and du by du is 1. So this is sine, y of u is sine of alpha pi divided by pi d by du of integral from 0 to u f of x divided by u minus x raised to 1 minus alpha dx. Okay, now you see here, see when we started with this, I have taken here y of t, no? So whatever solution we get, we will write it as y of t. Just now what I got is in terms of u. Okay, let me write it in terms of t. So what I will have to do, wherever there is u, put t. Okay, so I will do that, and we will get the final solution of this Abel integral equation. So I have got this y of u, let me name it as equation 3. I will rewrite this in terms of t. So that will be y of t equal to sine of alpha pi divided by pi d by dt of integral from 0 to t f of x dx divided by t minus x raised to 1 minus alpha. Okay, so this gives us the required solution of the above singular integral equation. Okay, so this is the y of t that we were searching for. So I'll stop here.